Okay. Okay, so with the mic, maybe it's more effective. The session is starting. People out there, please. Let's get started. So, welcome to this session, and our first speaker is Jendrik Seipp on subset saturated cost partitioning for optimal classical planning.
Welcome, everybody. So, what is this talk about? Well, the setting is optimal classical planning. And as usual, we want to use an A-star search with an admissible heuristic to solve this problem. And usually one heuristic is not enough, so we compute multiple heuristic, and then the question becomes, how do we combine the estimates? And we could maximize over these estimates and still be admissible, but a better option is to use cost partitioning, which distributes the cost of each operator among the heuristics, such that the total cost does not exceed the original operator cost. And one way of finding such a cost partitioning between several heuristics is saturated cost partitioning that we introduced some years ago. And saturated cost partitioning works by ordering the heuristics sequentially and then going over them and giving each heuristic as the minimum amount of costs that it needs to preserve all estimates for all states. And then it uses the remaining costs to treat the other remaining heuristics in the same way. So what we propose here, to give away the whole talk, is to only saturate for a subset of states, and this results in what we call subset saturated cost partitioning. So to get you all up to speed, let me first introduce you to saturated cost partitioning as it was introduced. So as I said, we order the heuristics, and then for each heuristic we use the minimum costs that preserve all estimates for this heuristic, and we use the remaining costs for subsequent heuristics. And for example, if we have these two abstractions here, this is one abstraction, this is the second abstraction. They have 5 concrete states, but only 3 abstract states each. There are 4 operators for different ones, and the top ones cost 4, the bottom ones cost 1. And so if we compute the heuristic and then we maximize over these 2 heuristics for the state S2, we would get an estimate of 5 plus 5 and 4, which equals 5. But we can do better with cost partitioning. And the way we do this for saturated cost partitioning is we offer all the costs to the first heuristic, and then we analyze which costs we actually need. And we can see here that, for example, here we don't need the whole cost of 4. Actually, here we do need the cost of 4, but here we don't need the cost of 4 because this operator only costs 1. So what we can do is we can reduce the costs here from 4 to 1 and from 1 to 0 here, and still have all the original goal distances preserved. And then we can use the remaining costs in the second abstraction. So we have 3 here and 1 here, and when we analyze this, we could actually preserve these costs as well and use 0 here and use these for other heuristics. So what we get in total is we get an estimate of 5 here and an estimate of 3 here, so a total estimate of 8 for state S2. So the basic principle that the saturated cost partitioning algorithm works on is finding these saturated cost functions, like we call them. And they have 2 requirements. The first one is that the saturated cost function for each operator is less than or equal to the original costs, and that we preserve all estimates for the heuristic under the new cost function so that they are equal to the estimate under the original cost function for all states in the concrete state space. And in this work, what we change here in this definition is that we say we only require this saturation for a subset of states in the concrete state space. So what we introduce here is 4 saturators, what we call them, that are functions that take the original cost function and produce a saturated cost function. And they differ in how many states they consider and for how many states they preserve the estimates. So the first one, obviously, is the one that we used in earlier work, namely the one that preserves all estimates. So here we have a second running example, and the way in which we can compute such a saturated cost function for all states is that we compute, that we use this formula here. And namely, we go, for each operator, we go over all transitions that this operator induces and compute the maximum of the state from the outgoing state minus the goal distance of the incoming state. So, for example, for the yellow transition here, for the yellow operator, there's only one transition, and we compute 1 minus 0, which equals 1, so we need the full costs to preserve this estimate. For the red operator, we need the maximum over 2 minus 1 and 1 minus 2, so 1 and minus 1, which says, okay, we need the full costs of 1. For the blue operator, we need 2 minus 1 and 0 minus 0, so we also need the full cost of 1 here. So the original saturated cost partitioning algorithm would allocate the full costs in this example to the first heuristic. So here we only have a one heuristic. But you can already see here some kind of problem because this state, for example, is not even reachable. And we are using it to compute, to preserve costs. So this is what our second saturator tries to overcome, and we call it the reach saturator. And it works by removing all unreachable states and their adjacent transitions, and then invoking the original all saturator. So let's do this. We remove the state below here, and then invoke the all saturator, which now can give this operator a cost of 0 without reducing any goal distances. Okay, so we still see, for example, if we are only interested in the heuristic value for this state, we are still giving costs here, even though we don't actually care about the heuristic value for this state and all the states that it represents in the concrete state space. So we introduce another saturator, and we call it the perim saturator. And it works by defining a perimeter around the goal states of a certain length k. And in our experiments, we just use, we set k to the heuristic estimate for the state that we are interested in. Usually we are only interested in one state. So what it does is we define this k, and then we cap all distances at most k. So let's do this. We reduce these two estimates from 2 to 1, and then we just use the all saturator again. And what this does here is that we now only have 1 minus 1 and 0 minus 0, so we can assign a cost of 0 here, and also for this red operator, a cost of 0. So we only use the costs that we actually need to preserve this estimate. And but in general, this might preserve more costs than we actually need if we only care about one state. So, for example, here we might have other states, and we might preserve the estimates even though we don't actually care about them. And this is our last saturator that takes care of this problem, and it is all about preserving only the estimates for a single state. And we do this by introducing an linear program, and the linear program is quite simple. So what this does is the first two constraints simply say that all heuristic values encoded by this h, these h values, are lower bounds on the actual goal distances under this cost function that is encoded by the c values. And this constraint defines that we actually use at most the original cost of each operator. And then we can just say the heuristic, the goal distance of the state that the concrete state is mapped to should be preserved. And here you can see we could preserve only the estimates of a single state, but we could also add this constraint for multiple states, and in this way preserve multiple states. So what this does for the example is we first remove all the unreachable states so that all values here are finite, and then it produces essentially the same cost function as before. We only use the value for the yellow operator. When we use this all saturator and also the perim saturator, something changes when we look at the space of cost functions that can actually be produced. The all and the reach saturator, they always define a minimum saturated cost function, and the one is a unique minimum saturated cost function. But this is not the case for the perim and the LP saturators. And you can see this when you look at this example where we have these three states and three operators, and we want to preserve the estimate for S1. Then all cost functions where the cost for this operator and this operator sum up to 1 will be minimal for preserving S1, because this distance is 1. And what this means is that we have now a large Pareto frontier of cost functions that we can choose from, and it's quite difficult to choose a good one. And to make sure that we are not worse than for example, a different saturator, when we use the LP saturator, we introduce the notion of chaining saturators. So we can compute the saturated cost function under one saturator first, and then use the produced cost function as input to a second saturator, or even a third saturator. For example, here, when we compute the reach saturator and then the perim saturator, we can first do the reach one and then the perim saturator. Okay, of course we also implemented all this, and in our experiments we used the usual limits of 30 minutes and 3.5 gigabytes for memory. We experimented with hill climbing and systematic pattern databases and Cartesian abstractions. And we evaluated this method both online and offline. And what this means is online we compute saturated cost partitioning for each evaluated state. And offline is the method that was traditionally used, where we compute multiple saturated cost partitionings offline before the search and then maximize over these estimates during the search. And we do this in the non-negative and general cost setting to evaluate this impact as well. So in the online setting and with non-negative costs, this first experiment analyzes the heuristic estimate that we actually get from these different saturators. So we have these 4 basic saturators here, and the chained saturators with 3 single saturators with LP chained after them. And we compare how often they produce better estimates than a different version. So for example, how to read this slide is here in 15 of the in total 1,506 tasks that were solved by both methods, the reach saturator produces a higher estimate than the all saturator. And in only 2 tasks, the other way around is the case. So the reach saturator has only a mild impact on the heuristic estimates. When we use the perim saturator, on the other hand, it has a big impact. So in 430-something tasks, they are better than the all and reach saturator. And we can see that the LP saturator is also a little bit better in some cases, but it has a larger variance. So, and this is due to this large Pareto frontier that it can choose from. When we stabilize the LP saturator by chaining a different saturator in front of it. This behavior is reduced somewhat, so it is better in more cases than not. And in total, we can see that we actually improve a lot upon the state of the art, the previous state of the art. In 512 cases, it's better to use this new chaining saturator instead of the all saturator. And if we look at the runtime and the coverage of these methods, we can see that the LP-based saturators are much slower than the ones that don't use LPs. So here we have the evaluations per second in the non-negative and the general setting. And we can see here we evaluate 1,000 states per second, and here only at most 10. And we can also see that we solve more tasks when we use the perimeter saturator than the all saturator. And we see that using general costs pays off, usually, instead of non-negative costs. So we now analyze the second scenario, where we compute saturated cost partitionings offline before the search. And here the results are quite different. The first thing we notice is that the LP saturator is still the worst because it's just too slow, even in the offline setting. And what we also see is that the all and reach saturators perform almost equally. There's only one domain where all solves more than reach. And the perimeter saturator is quite worse than the all and reach saturators. So there's one domain where perim solves more tasks than all, but in 9 domains, all solves more than reach than perim. And this is due to the case that these offline computed saturated costs partitionings consider sample states. And all the states that are not in the perimeter of this sample state are ignored, and we throw away these costs. So what we can do instead is we can compute the perim saturator first, and then compute another saturated cost partitioning using the remaining costs after this perim saturator has been used. And we call this version perim star, and it actually improves upon the state of the art. In 4 domains, it solves more tasks than the all saturator, and it's worse in only 1 domain. Cool. So in summary, we presented a generalization of saturated cost partitioning by saturating only for a subset of states. We proposed 3 new saturators that do this and showed that they yield stronger heuristics. But thank you very much.
Okay, we got time for questions.
So thanks, nice talk. This is more of a general question. Over the last few years, there were really many works that, without changing the underlying heuristics, but just working on the cost partitioning, showed that you can really improve the performance of optimal planners a lot. So do you think this will continue like that? Or are we approaching some limits, or is there really so much more you can do with cost partitionings to get better estimates for the search?
Yeah, good question. I think there's still lots to do on both sides. So you can use better abstractions and get higher estimates, but there's also still lots to do on the cost partitioning side. I think there's lots of options, and we will hear about these in a later talk, I think.
I have a question about the ordering. So it seems to be order dependent on how you order heuristics. And if you have 1,000 heuristics, you have like permutation of 1,000, many options to do cost partitioning.
Yes.
Is there any way out of that?
Yes, so we have proposed a method that tries to order the heuristics first that have a high heuristic estimate for the state that you're considering, but use relatively low costs for preserving this. So doing this method, doing this greedy ordering, you actually are much better than just a random ordering. Come again? And you can also optimize in this space of orderings. So you can start with a random ordering and then permute them and do, for example, this in a hill climbing method.
Okay, I have one more, hopefully short question. So when you do this reachability thingy, for example, online, apparently you can lose information when you show those cases where the initial state heuristic value was smaller. I don't understand where this information loss occurs. I mean, if you just throw away things that are unreachable, why do you get a smaller heuristic value?
This can be the case because the method is greedy, and it does not always pay off to have higher costs, but usually it does.
So it might be like interactions across the different...
Yes.
Okay.
Yes.
Any other questions? Okay, let's thank the speaker again. And our next talk has a long title that I'm not going to read off, and please begin.
Okay, thanks. So I will read it out, I guess. So this talk is about counter-guided abstraction refinement for pattern selection in optimal classical planning, which is work that mainly Alex has done during his bachelor thesis, and which is also joint work with Malte. Okay, so the setting we are in is we are interested in pattern database heuristics, in optimal planning, and as you might know, usually we don't compute a single PDB because these don't scale enough. So we usually compute pattern collections and then based on these pattern collections compute a set of PDBs. So there's two questions that we have to ask here is the first one being how to combine the resulting PDBs in the end. And there's quite a few of methods out there, one being, for example, the canonical PDB heuristic that dates back to 2007. And another one that we just seen, the cost partitioning methods, such as saturated cost partitioning, which we will actually also use in this work here. And the second question we have to answer for computing pattern collections is how to actually select these patterns for our collection. And again, there's quite a few methods, and two of the most successful being based on hill climbing in the IPDB setting, and the other one using a combination of genetic optimization and bin packing to compute complementary pattern collections. And in this talk, we are focusing on this pattern selection problem. So what got us there in the first place was the observation that both of these methods, so hill climbing and genetic optimization, they can be somewhat slow. So we usually use them with a time limit in order to make sure they don't use too much time. And so we wanted to come up with a simple but also fast pattern selection method. And to this end, we used the CGAR principle, and the resulting method is very fast, and it only considers useful because causally connected variables for pattern selection, and it also has convergence guarantees. Okay, let's start with having a look at the actual algorithm. So as a first step, we were concerned with computing a disjoint pattern collection as to make a compromise between only computing a single pattern, which would be very fast, and computing an arbitrarily large pattern collection, which is just a very huge space. And that means that if we compute a disjoint pattern collection, we only have to consider each variable at most once, which simplifies lots of things. So how does CGAR work? So we initialize our pattern collection C by adding one pattern for each goal variable, as it is done in the IPDB algorithm, for example, also. And then we repeat the following steps. First, if we haven't already done it, we need to compute an abstract plan for each pattern in our collection, which can be easily done because having the PDB computed means that we have a perfect heuristic for that projection. So that means that we make an attempt at solving the problem in the abstract state space. Then what we want to do is we want to check if these solutions already present a solution in the concrete state space, and that means that we apply all of these abstract plans on the concrete planning task, and if they fail, which they will do most of the times, then we collect so-called flaws. And the flaw in our setting here is, for example, that an operator from the plan cannot be applied because one of its preconditions is violated, and this is the case because the pattern doesn't know about one of the variables mentioned in this precondition, and that is, we always have flaws of the kind that some of our patterns in our pattern collection is lacking a specific variable. So we can compute a list of these flaws, and what we then need to do to continue with the overall process is we attempt to refine our collection in order to avoid the same flaw from occurring again in future iterations. And that is that we need to introduce the missing pattern to our pattern collection, and more specifically, to add it to the pattern which is lacking the variable. And since we want to compute a disjoint pattern collection, that means that if the variable is not present in our collection yet, we can just add it to the pattern, but if it is already in the pattern collection, we need to merge the two patterns in question, which is, of course, somewhat expensive. And we can do this until we run out of time or memory, or until we actually solve the planning task by having computed an abstract solution which works in the concrete planning task. Okay, that was the basic algorithm. Very simple, very fast. But of course, disjoint pattern collections are not very informative, so in the end, we do not want to have this restriction. We want to be able to compute any type of pattern collection. And to do so, what we simply do is we repeatedly, and many times, run this algorithm to sample different pattern collections, and then we just combine them. And to make things even simpler, the first thing we did is to restrict the above algorithm that we've just seen to compute a single pattern by just running it on a task where we only consider one goal variable to be present. And in order to ensure that subsequent calls to this SIGA algorithm actually produce different patterns, we also considered two additional techniques for diversification, one being to randomly exclude some variables called blacklisting, and another one being the stagnation, where we keep track of whether we actually still generate new patterns or not, and can abort the algorithm early on or switch to blacklisting. Okay, let's have a look at some experimental results. So these are the baseline algorithms we considered. There's more data in the paper. The first one, SIS2, is just a systematic enumeration of all patterns up to size 2, which is very fast because there's no difficult logic involved, so it runs in a very short time on average, but it also doesn't achieve a very high coverage, but still, surprisingly, maybe to some of us, higher than the hill climbing algorithm, which runs for 900 seconds. And the last algorithm we compare against is the complementary pattern collection algorithm, which we actually only ran for 100 seconds because that yielded much stronger results compared to running it for 900 seconds. How do our methods fare against this? So here we see that the single SIG algorithm cannot quite compete yet in terms of coverage, but it is very fast as intended. And once we run this algorithm repeatedly using the multiple SIGA algorithm, we actually can achieve quite a bit of higher coverage compared to the competitors, and still in a reasonable amount of time. And this gets even better once we use our diversification methods in addition. Okay, I think it's time to conclude. So in this work, we use the SIGAR principle for generating pattern collections, which is a very fast algorithm, which actually results in state-of-the-art pattern selection in the explicit PDB settings, we have to say, and also only until Jendrik will present his new paper at ICAPS this year. And in future, we would like to further improve on this by, for example, interleaving pattern selection with the cost partitioning heuristic itself. Thank you.
Questions? I think, unless somebody else wants to say something, I find it kind of funny that, I mean, it's so obvious an approach to use, you know, CGAR, we use it everywhere else, that it has taken until 2019, right? So apparently people before had reservations about this idea. Can you maybe say what those were and if you feel you have refuted them now? Or?
I don't know. I personally didn't have any reservations, I think. But I guess some reservation might have been that PDBs are not as well suited, like Cartesian abstractions, where you can naturally refine them in an easy way, let's say. But since we compute many patterns here, I guess this problem can just be, well, quite neglected in some sense.
The refinement operations are limited, yeah,
yes.
But that doesn't seem to be a problem.
Yeah, I think a lot more can be done there. Like it took us 5 years to just put a time limit on IPDB, and that increased like the coverage by 100, right? Don't just keep on. At some point, please start planning. I think there's a lot more that can be done there. Other simple ideas that haven't been tried.
I just want to sort out things a bit. This CGAR is actually the name that came from the verification and from Susanne Graf and others that did lots of things. What I'm interested in is CGAR itself. It's here combined with pattern databases, and the thing with the Cartesian abstraction, this is not pattern database. So CGAR does work on both.
Yes.
So, and in this paper, it does work only on the pattern database, is that?
Exactly. So CGAR is really just like a method where you have the general idea that you start with some abstract solution, which is very coarse in the beginning, and then you try to refine it. And you can use probably even other abstractions, maybe even merge shrink, who knows.
Okay. And now to conclude this, Jendrik, can you please tell us what your even better pattern databases are doing then?
Okay, if you ask. Well, the new method combines saturated cost partitioning with pattern selection. So what you do is you loop over a set of patterns, and you already check each. You do the saturated cost partitioning during this analysis. So you add the first pattern to your selection, reduce the costs, and then compute the next projection and see are there any costs left in this projection. If there are, you add them to the collection. Otherwise, you discard it. So it's a pretty simple method, but it works really well.
Okay, cool. And any other comments on this actual paper here? Okay, so let's thank the speaker. And our next paper is on an empirical study of perfect potential heuristics, and please go ahead.
Hi everyone, I'm Augusto. This is a joint work with Florian. We are going to talk a bit about potential heuristics here, and well, a bit more. So to give some context, we're talking still about optimal classical planning, and the main goals of my talk or in the paper is to learn more about the topology of the state space of different domains, especially IPC domains, and we do that by studying the characteristics of the perfect heuristic in these domains. And as a second goal, we'd also like to understand the limitations of potential heuristic in many of these domains. So a bit of background, we are using factor state representation, so states are sets of facts, and we also consider that features are also sets of facts. So we say that a feature is true in a state if it's a subset of the state. So intuitively, a feature is basically talks about the interaction of facts in this task. And from this definition, we can also define what we call a potential heuristic. So in a potential heuristic, we have a weight function and a set of features. And what it basically does, it's associate this weight function to each feature. And to compute the heuristic value of a state, we basically sum the weight of every feature that is true in a given state. And one important characteristic is what I call the dimension of a potential heuristic, and that's basically the size of the largest feature used. And basically, a potential heuristic with a high dimension means that we have very complex interactions between facts. We are taking into account many high-level interactions between the facts. So one thing that you can see in this definition is that if you have a state that is unsolvable, in classical planning we usually define that heuristic value of this state should be infinity, but these potential heuristics don't handle that. So what we do is we have this new definition where we actually have two potential heuristics. One potential heuristic, in this case, we have two weight functions, one is W1, one is W2. So this makes two potential heuristics, one of them just to capture unsolvable states, and one of them to really estimate the distance. And we say that this potential heuristic is a perfect potential heuristic. If one, it is perfect for all, so in all solvable states, we can really estimate the true distance to the goal, and for all unsolvable states, we can capture, we can sign them as unsolvable. So one cool metric in potential heuristics is what we call correlation complexity. This is back from satisficing planning. And we extend it to optimal planning here, what we call optimal correlation complexity. And basically, the optimal correlation complexity of a planning task is the minimum dimension that a perfect heuristic must, perfect potential heuristic must have in this task. So this gives us some insight about the complexity of the interaction among the facts of this planning task that a heuristic must take into account to be perfect for all states. And we would like to study this optimal correlation complexity measure over the IPC domains, and we do that empirically. So we compute empirically, try to find perfect potential heuristics for many IPC domains. And it happens that this problem is very hard, because first, we can only do that if you already have the whole state space marked with the perfect heuristic for for all states. We also need to know the good set of features that we want to use for our potential heuristics, and we also need to know how to find this weight function associated to that. So we come up with some methods just to study this topology and this characterization of the perfect potential heuristics. And the first method is what we call the exact methods. It works both to capture unsolvable states and also to estimate the true distance between states to the goal. And basically what they are linear programs over the whole state space. So it gets the whole state space as input, and also gets an initial set of candidate features for the potential heuristic. It creates an LP and it tries to solve that to try to find a perfect potential heuristic. If we cannot find a perfect potential heuristic with our initial set of candidate features, what we basically do is we add more features to these candidate features. And the cool thing about this exact method is that once we find a perfect potential heuristic, we know that this is the optimal dimension potential heuristic for this task. So there is no perfect potential heuristic with lower dimension than the one that we found. We have some experiments to analyze this first part. We obviously use fast downward. That's the setting, 10 minutes and 3.5 gigabytes. And a bit disclaimer here, since we can only handle tasks where you can have all this state space, because we need that as input, then our sample size is considerably small. We only have 301 tasks here. And so take these results with a grain of salt. So first, we have the distribution of the optimal correlation complexity over these 301 IPC tasks. And we can see here that many tasks really have a low optimal correlation complexity. So this means that we can have a perfect potential heuristic there, not considering many interactions. However, we see that we already, even though these are very small tasks, we already have very complex potential heuristics, that perfect potential heuristics here, and we expect this, if we could handle even larger tasks, to go even further. So like, we expect that probably would have unbounded optimal correlation complexity with allowing larger instances. If you check that in a domain-wise measure, here what we are checking is per domain, we check what we call lower bound. So for example, for Gripper, what we have is a lower bound of 7. So this means that in Gripper there was at least one instance where we had the optimal correlation complexity of 7 for the perfect potential heuristic. So we know that Gripper, if you want to have perfect potential heuristic for the whole domain, we have a lower bound of the optimal correlation complexity of 7 for that. So you can see in this table that for very simple domain like Gripper, like visit all, we already have to consider many interaction between facts, so have a very high correlation complexity. And an interesting thing is that if we restrict our potential heuristic not to be perfect in the whole state space, but only in the reachable state space, then the functions get significantly less complex. This sounds good, but in practice, most of the methods that synthesize potential heuristics cannot handle that. They don't have this information. So yeah, it's not as good as it seems. But the cool thing is that if you isolate only for the try to find a potential heuristic that only captures unsolvable states, then the functions get significantly less complex. So in our benchmark, we could always find potential heuristics to perfectly capture all unsolvable states with dimension up to 3. And another question that we try to solve is how close can we get to the perfect heuristic if we limit the size of the features that we can use. And for that, we have a greedy method. That's this minimal error for finite values. So basically, what we do is we start with an empty potential heuristic, so have no feature and no weight function. And then we check for all features up to a given size, which feature we could select that would reduce the error the most. And by error, we simply mean the sum of the difference for all states between the heuristic that we currently have and the perfect heuristic. So we keep doing that, and once there is no feature that reduces the error, we simply increase the size of the features that we're considering, so increase our candidate of features. And what we can do now is that we can have some cool plots like that, that at every line is one instance. So basically what it shows is that for every feature, the x-axis is the number of features selected, and the y-axis is the error, so like how the error decreases as we select more features. And one cool thing that you can see here, at least in this curve, I don't know if you can see this curve, but it repeats in most auto tasks, is that we have this smooth decrease, and then out of nothing we have this sudden, very quick decrease. And these are especially the parts of the our algorithm where we increase the size of our features. So in practice, the behavior that you see here is that if we select only very few features of a given size, they are already enough to give a lot of information to our potential heuristic. So we don't really need many features of the same size, only need a few of them to make our heuristic very informed. So just to wrap it up here, what we did basically is we studied the shape of the perfect heuristic in several domains using potential heuristics, so the perfect potential heuristics as we call it. The bad news is that even for very easy domains like Gripper, Visit All, perfect potential heuristics are very complex already. But the good news is that we also found out that if you only select a subset of very large features, this is already enough to give you a lot of information to your heuristic. And this is good news because if you can automatically come up with a method to find these large features, then you could use a fixed parameter tractable algorithm to find good weights for them, and then we could really use that as a heuristic. That's it from my side. Thank you very much.
Questions?
Thank you for a great talk. So how do we find those interactions efficiently?
So in our case, or like?
No, in general.
Yeah, that's the open question. I would like to have the answer, but I don't.
Hi, thanks for a great talk. So the size of the number of candidates is exponential on the optimal correlation complexity. That's.
Oh yes.
Okay, so how do you find the initial candidate set?
So what you do is we generate all candidates up to a given size. So we start, for example, we start actually with size 0, might be a constant without any variable, and then we increase to size 1, and then we consider all features of size 1. Then if there is nothing that decreases our error, we increase size 2, and so on and so on.
Can I have another one? So you said that you need a small number of features of a big size. Mm-hmm. Can you comment on which have we looked? What do they contain? Like for a specific problem, for example.
There are many. So if you allow very large features, of course, you have features that are representing states, right? But basically, there are many general cases that are able to be captured by like very simple features, but then there are some domains where corner cases really need like large features, and then once you have a feature large enough to capture like some peculiarities of the domain, then you can really decrease that. But I don't have in mind any specific example. Actually, one in Gripper that we had that is very complex is the case where basically you're computing features that handle states where mutexes are violated. So, because you're considering the whole state space. So, for example, in Gripper, we had a feature that had to handle the robot carrying itself or something like that. And yeah, that's tricky, but depending on the method that you are using to synthesize potential heuristics, you don't really have better options than to consider the whole state space.
I'm just curious, how many million CPU hours have you burned for that?
How many, what?
How many CPU hours?
Ooh, that's a good question. So we use it fast downward, so like most of these instances are very small. That's one thing, so like they have already the state space, and I think if we didn't put a time limit of 30 minutes, we'd still be running some LPs because they're so large. But yeah, that was.
So is it more million or just?
No, it was not that. I mean, it was less than that. I wouldn't have a proper number, but it was feasible time.
Okay, yeah. Lots of stuff to discuss still in the coffee
Yes.
break. Let's thank the speaker again. And so I'm glad to announce the best paper presentation in this session. And Florian, please tell us all about it.
Stop my timer. Okay, thank you. So this is joint work with Gabi, Malte, Hadrien, LouisMartin, and Domenico. We talked about this at Dagstuhl seminar early last year, and we saw a relation between Lagrangian decomposition and optimal cost partitioning for classical planning. So I we'll start with a description of what Lagrangian decomposition is, and I apologize in advance. This is going to be very technical and very mathy. I heard that every formula in your slides halves the audience, so I'm glad that there are more than 64 people here, because the first 6 slides are going to be formulas. But after that, I hope I will bring it back to something much more intuitive. And I think this first part is the main interesting part of that, so I think it's worth going into the technical details here. After that, I'm going to talk about how this relates to cost partitioning, and in the end come up with an algorithm that solves optimal cost partitioning without using an LP solver. So it's an anytime algorithm that can come up with an optimal cost partitioning, but not with a classical route through an LP solver. So let's start with Lagrangian decomposition. And this is a technique from OR, where we want to solve a linear program. So a linear program minimizes or maximizes, in this case, minimizes an objective function, a linear function, c times x, subject to some constraints. And we can group these constraints, or we can write these constraints as a matrix multiplication of a times x larger or equal than b. And here we just group them into k different groups. So think of each of these blocks, a1 times x1 larger or equal than b1, as a set of linear constraints. So the decomposition part, the first thing is just a rewriting of the problem. That all of these constraints depend on the variable x, but otherwise they're independent. So to make them more independent, we are introducing a new variable xi, and using one set of variables for each of the constraints, for each of these blocks. Of course, if we want to change the problem, or if we want to use this new variable, we still want to solve the same problem as before. So we have these additional constraints, x equal to xi, just to make sure that we didn't actually change the problem, that this is a pure rewriting of the problem. Okay, so here's the same problem again. And everything still depends on each other. So it's still not a decomposition, because we cannot solve these blocks independently. So right now, we are doing a step that's called Lagrangian relaxation of these constraints x equals xi. So you can see that on the right-hand side, the constraints x equals to xi disappeared from the problem, but instead the objective function changed. We have new terms in the objective function that give a penalty whenever we violate this constraint. So when x is equal to xi, this term is 0 and the objective function doesn't change. But if we violate this constraint, the amount by which we violate it is multiplied by this penalty term, lambda I, and is added to the objective function. And these penalty terms are called Lagrangian multipliers. Think of them just as numbers that are parameters of the problem. So the new problem is p of lambda. And for every choice of these lambdas, the solution of the original problem is still a solution of this p of lambda. And so it has the same cost. And so p of lambda for any specific choice of lambda gives you a lower bound to the original problem. And since it's a lower bound and we can have different lower bounds, an interesting question is what is the best lower bound we can get? So this problem of finding the best lower bound is called the Lagrangian dual problem, where we treat these lambdas as variables, the Lagrangian multipliers, and try to find out for which choice of lambda do we get the best lower bound. And in this case, under some mild assumptions, you can say that the best lower bound is actually perfect. So the solution to the Lagrangian dual problem actually solves our original problem. Okay, so now that we did this relaxation, we can actually come back to the decomposition part, that the constraints are now completely independent blocks of constraints. So the ai times xi larger or equal than bi part doesn't interact with each other. So we can split this problem into one problem per I and one additional problem that depends on this variable x. So the part that depends on the variable x, I don't know if that works, yeah. So c times x depends on the variable x, and then for every lambda I, we have a term minus lambda I that also depends on x. But none of these constraints actually restrict the choices for x, so we just have the constraint that x cannot be negative here. For the problem that depends on x, the part that depends on xi is just the term lambda I times xi, which we get here, and one of these constraints, the one for I. So we have these independent constraints. Let's look at the first one in particular, the one for that depends on x. So this problem is minimizes a combination, a linear combination over the variables x, and so these are all fixed numbers, and if they are all non-negative, then the best we can do is just set all x's to 0 because we can't make them smaller, and then the value of this problem will be 0. If one of these constraints, if one of these coefficients is negative, then we can actually set x as high as we want, and it will get lower and lower values, so the problem will become unbounded. And this means that the solution to this problem is either 0 or it's unbounded. If it's 0 if we satisfy this constraint here, that the coefficients are non-negative. And we can, instead of viewing this as a subproblem of the decomposition, we can just view it as an implicitly defined constraint. So how does this relate to cost partitioning? Let's first put all the previous part together. So this was the original problem we started with. We minimize an objective function subject to some blocks of constraints. And we solve this by Lagrangian decomposition, which means we have a Lagrangian dual problem that maximizes the multipliers, the value of these lambdas, the penalty terms, subject to this implicitly defined constraints that the sum of the multipliers have to be less than or equal than c. And the thing we're maximizing is the sum of these subproblems. And the subproblems themselves just have a single one of these constraints and one of the multipliers. And now this is the part where we go back to the planning world. If I just rename everything a bit, this looks very much like cost partitioning. In particular, cost partitioning over operator counting heuristics. So our original problem, I specifically grouped these constraints into blocks because this is what operator counting does. It minimizes the total cost, where x counts how often an operator is used, subject to some operator counting constraints. And each operator counting constraints can be a group of constraints. This part up here exactly looks like cost partitioning, where we compute heuristics under their own cost function, with the only constraint that the sum of the cost function cannot exceed the original cost function. And finally, the subproblems are again operator counting heuristics. They look exactly like this, just for this specific cost function and for only one of the constraints. Okay, so this relation of cost partitioning and operator counting is not new. This is something we knew already. The new thing is that we now know that it relates to a Lagrangian relaxation, a Lagrangian decomposition. And that means we can use all the techniques developed for Lagrangian decomposition and apply it to cost partitioning. So one way that the OR community uses to solve Lagrangian decomposition is by subgradient optimization. And the reason why we can do this is because this Lagrangian dual problem, the P of lambda, is always concave, and we want to maximize it. So subgradient optimization, I mean, actually it's the opposite way. It's for convex function that we want to minimize, but that's just flipping everything. I'm going to flip to that now because that's the more common way of explaining this. So just a quick intro of what subgradient optimization is. It's very similar to gradient descent. You can choose a point in the definition space of the function, compute a gradient at that point of the function, and then go into the direction dictated by that gradient for a certain length, get to a new point, compute a gradient there, and continue on. For subgradient optimization, there is one special case that you can see here. At that point, the function is not differentiable, so it doesn't have a gradient, but there are several subgradients. You can think of them as just lines that stay below the function. And interestingly, it doesn't matter which one we pick. As long as we pick one of these subgradients and, again, make a step according to the step length function in that direction, we'll end up with an optimal solution eventually. And there are some restrictions on what kind of step length functions we can take. They have to be decreasing, not too fast, not too slow, but those are very mild restrictions. Another problem is that in this particular example, if our first step length would be too large, we would step outside of the definition space of the function. And there is also no gradient because the function is just not defined at that point. And there's another surprisingly easy fix for that. You can just project the point back to the definition space of the function. And that is called projected subgradient optimization. Okay, so let's apply this to cost partitioning, specifically cost partitioning over abstractions, as Jendrik and Silvan talked about. So the things we need to interpret to apply this is what does our current point mean in the subgradient optimization, what is the subgradient, and how do we do this projection. So the current point is just a vector of these Lagrangian multipliers, which, as we saw, are just our cost functions for the individual problems. So think of these as just one long vector, but grouped into these k parts, one cost function per subproblem. The subgradient, interestingly, is just an optimal solution of a subproblem at the current Lagrangian multiplier. So if we view the subproblems as abstraction heuristics, the Lagrangian multiplier is a cost function. An optimal solution to that cost function is an optimal operator count under the current cost function. And for abstraction heuristics specifically, this is just an optimal plan. So we compute an optimal plan in the abstraction, count how often an operator occurs in that plan. And this is our subgradient, and we can just add this to the cost function. Of course, if we add stuff to the cost function, the cost functions will not form a cost partitioning necessarily, so this is what the projection does. We have some cost functions, they don't necessarily form a cost partitioning, and we have to reduce the costs enough to project them back to a cost partitioning. Okay, so this is the anytime algorithm that you can use to get to an optimal cost partitioning. You can start from any cost partitioning that you want, and then repeatedly just loop over the abstractions. For each abstraction, find an optimal plan under the current cost, then count how often each operator occurs in this plan, add this number to the cost, which is kind of surprising. You're adding a count of operators to a cost, which seem to be unrelated, but also intuitively makes sense because the more you use an operator, the higher you make its cost. Of course, this gradient, again, is multiplied by a step length that decreases over time. And if you just repeat this, it's ending up at the cost partitioning. And like I said, it can happen that you step outside of the space of definitions, because if you add something to a cost partitioning, you can violate the cost partitioning condition. You can use too much of the cost of an operator. So in between each step, you have to project it down to a cost partitioning. But all of these steps are independent of an LP solver, and all that it requires to do is finding optimal paths in an abstraction, which we really know how to do. Okay, so we tried this out in some initial experiments. We used IPC tasks, projected them to interesting patterns of size 2. There are some more results in the paper, which I'm not going to talk about here. We unfortunately only know how to do this for non-negative cost partitioning, not for general costs, where the costs can be negative. While the heuristic values are better with general costs, we don't know how to project a cost function, a set of cost functions, to a general cost partitioning. It's easy to do for non-negative cost partitioning, but for general cost functions, this is complicated. We used 5 minutes of time and 2 gigabytes of memory, and we only considered the heuristic value of the initial states, because for now we just want to see if the technique itself works. I said we can start with any cost partitioning, so we started with uniform cost partitioning, opportunistic uniform, greedy zero-on, and saturated cost partitioning, which are some state-of-the-art suboptimal cost partitionings. And the last 3 of them depend on an order, as we heard before. So we tried both a random order and an order that we improved for, I think, 100 seconds. Okay, so to view the results, I'm going to show them in this plot. This just shows so for each task we compute the ratio of the heuristic value versus the heuristic value under an optimal cost partitioning, and then we just use the geometric mean. So for example, this line here shows that uniform cost partitioning has about 55–58% of quality. Now if we add other static cost partitionings, you can see that saturated cost partitioning already improves on that. Opportunistic uniform also works well. Greedy 0–1 doesn't deal so well with random orders, but if we improve the order, you can see that all of them have a much better quality after some hill climbing, after some time improving the order. Okay, now the x-axis shows iterations of these anytime algorithm that I mentioned that just use this subgradient optimization to improve the cost partitioning. And here, for example, for uniform cost partitioning, you can see that it improves over time, the quality improves over time quite nicely. And after maybe 100 iterations, it already exceeds the quality of even the improved saturated cost partitioning. And this trend continues if we look at the other cost partitionings. If we start with a better cost partitioning, the curve is higher, so it means that we get the benefit of starting with a better cost partitioning, but we are still able to improve it. And all of the cost partitionings at the end end up more or less at the quality, I mean, except this one just barely makes it in 10,000 iterations. But even if we start with a bad cost partitioning, we are able to improve it over time. And interestingly, it doesn't take that many iterations of the algorithm to get to really good cost partitionings. So we also wanted to analyze the runtime of this, but of course the runtime depends on how many iterations you do. We more or less arbitrarily picked 200 iterations because that seemed quite okay from the quality. And we compared this to just computing the optimal cost partitioning in one large LP. And you can see for 200 iterations, the payoff is quite good. So it can be much faster than computing the full LP. And yeah, it is able to finish much more often. Okay, so I already exceeded the time a bit, so I'm going to conclude by just saying we have a new view of cost partitioning, this time as Lagrangian decomposition. And this new view allows us to use techniques that were developed for Lagrangian decomposition. So, for example, in this case, we used subgradient optimization. And specifically, subgradient optimization leads to an anytime algorithm that can start with any cost partitioning and just improve it over time. In the future, I think there's lots of things we can try, specifically all the techniques developed for subgradient optimization. So particularly, we had a very stupid stopping condition. We stopped after 200 iterations. There's definitely better things to try there. Our step length function was the most naive thing you can think of. It's just 1 over the number of iterations. There's much research in that direction. And there are techniques that stabilize the gradient when doing updates and so on. We didn't use any of those, so there's lots of things to try there. From the planning side, an interesting open question would be how to project to general cost partitionings, which we currently cannot do. And finally, we have some issue with very high operator costs, or very different operator costs in particular. So if an operator costs 1 million, and we start the step length by 1, and we use an operator once in a solution, that means we add 1 to the cost in each iteration. And if we start very far away from an optimal cost partitioning, it takes a long time to reach this optimal cost partitioning. So that would be interesting to find out some solution for that. So with that, thank you for listening, and I'm happy to take any questions.
Okay, cool stuff. Questions? Okay.
So now that you cast this as subgradient optimization, have you thought about using something like TensorFlow to actually do this?
I haven't thought about it yet, but yes, I mean that's the nice thing, that it opens up a lot of options.
Yeah, nice work, nice connection. So one thing that you often will do when you're using this type of approach is you can get a suboptimality gap, you know, the difference between your primal and dual. Did you measure that and see how informative it is in your case?
Well, I mean, this plot kind of shows the optimality gap. So this is
I mean, the approach can give you an estimate itself of how far away you might be from optimal.
So we didn't measure this within the approach. We only measured this after the fact.
Okay, yeah. So it would be interesting to see that, because you get an online estimate of how close you are.
Yeah, so that would definitely be one of these parts that I mentioned at the end, that we need a better stopping condition, and that would go in that direction, yes.
So these methods really come up with a very good heuristic estimate, very close to this optimal cost partitioning. What I'm interested in at the very end, we also want like plans to be computed fast. Have you ever tried to implement this heuristic in generating a full plan? And how does this perform?
So we ran this on just using it as a heuristic. So these results are all just for the initial state, but we also ran it for a full heuristic. It isn't that good so far. So I think there are several reasons for that, and I think most of them are related to the fact that it's just a bit too early. Like we really tried the most naive choices for everything. One thing that is directly related to the stopping condition is that we always do 200 iterations. So we always keep the old cost partitioning and start from that. And if that's already optimal, doing 200 iterations is just a waste of time. And if we do the same thing with an LP, like solving it once is expensive, but the next time if we solve it, if it's already close to the optimal, it recognizes that and only does a few steps and is done. The other point where I think we are losing a lot on this front is that this is non-negative cost partitioning over some relatively small patterns. So it's not like the coverage even of the optimal cost partitioning is not that great to begin with. But I think like most of these problems are just problems that require more work. It's not a fundamental limitation of that.
There's a huge algorithm space that you have only begun exploring here. Any other questions or comments? Okay, so let's thank Florian again. So we're a little over time, but only a little because we had 10 minutes slack in this session from the outset. And our next talk is by Michael Katz. I cannot see the title yet, but it's on oversubscription planning, so it justifies the second part of the title of the session.
Hello. Yeah. Thank you. So first of all, I'm not affiliated with Basel, so this is just one of. But we do have Florian on the author list. So yeah. And the second point for this talk is not about cost partitioning. So this talk is about oversubscription planning, classical planning with multiple cost functions, and it's joint work with Emil, Keyder, Florian, and Domenico Winter, who was a summer intern at IBM at the time. But that's when this work started. So a little bit about the formalism. So this is a SAS formalism, which means multivariate variables, initial state, goal as a partial assignment, and actions of the form preconditions and effects when preconditions are defined whenever effect is defined. So it's SAS and not SAS plus. In classical planning, we have a non-negative cost function that assigns non-negative cost for each action. And a plan is an applicable sequence of actions that takes us from the initial state to some goal state. And in cost optimal planning, as you all know, we find one plan minimizing some action cost. So if we need to move from classical planning to planning with negative costs, then what changes is just this one thing that the cost function can allocate negative cost to actions. And here we actually need another thing. We need to introduce formulas for multi-cost functions. So planning task with multiple cost functions will have another component that will, I don't see here. that is basically a set of pairs of a cost function and a bound. And in this formalism here in this paper, we focus on, we call those secondary cost functions, and we focus on the secondary cost functions with non-negative costs. And this seems to be sufficient for our purposes here, but in principle, of course, you could have negative costs here as well. So plan would now be a sequence of actions that, in addition to being a plan for the classical planning task, will have an accumulated cost according to secondary cost functions under the bound. And the same is for the cost optimal planning. Basically, among the plans, you need to find one that will have a minimal summed cost according to primary cost function. So coming back to what we actually want to solve here, an oversubscription planning task was presented 15 years ago now by David Smith, here probably. And here the difference is that we don't have a goal, but what we do have is a state utility function that maps states into real numbers. And we have a bound on the summed action cost. And the plan would be a sequence of actions with a cost under that bound. And in oversubscription planning, the task is to find a plan that maximizing the utility of the end state. So the restriction that we have in this work is on additive utility functions that are basically sums over individual utilities of state facts. So how do we solve this? There have been several approaches over the years. Well, 15 years, there have been like 5 papers on this that were doing basically branch and bound with admissible heuristic functions. And the admissibility criteria here is not to underestimate. So you overestimate the remaining utility from that state. And trivially admissible heuristics would be, in our case of additive utility functions, is just sum of over all variables of the maximal utility per that variable. So there was a work of Vitaly Mirkis and Carmen Domschlag in 2013 that did an adaptation of a classical heuristic PDBs to this framework. And then they included landmarks into the problem in a year later. And then Erez Karpos and his student did work on extending that landmark encoding to improve it. The problem is that there is no automated code available for any of those works, so we couldn't compare to previous work, but we compared to baseline that I'll show you later. So the main contribution of this paper is 2 reformulations of oversubscription planning to MCF, to multi-cost function planning, that allows us to much easier adapt the heuristics for classical planning into heuristics for OSP through heuristics for MCF. So we have an example adaptation of a merge and shrink heuristic and an adaptation of a MCAT heuristic that we use here for experiments. And additional technical contributions are, first of all, there is now an open source planner available for OSP. There is, we extended PDDL in order to describe planning tasks for OSP. And there is a fast downward translator that adapted to understand that fragment of PDDL. And of course, we created a benchmark set that is also available, and you can try that in your experiment. Use that in your experiments. And in this talk, I will focus on the reformulations because that's the most interesting part, and I don't have much time. So there are two reformulations that we present here. The first one is inspired by soft goals compilation by Emil, Keyder, and Hector Geffner. And we also call it soft goals reformulation for some reason. So basically, in this reformulation, we add actions that allow to forgo achieving the goal by paying some penalty, basically. Right? So we add so this is not restricted to SAS, it's on SAS plus. You basically add one value for each variable, and this will be a goal value. And you add actions that are dependent on precondition on that value and achieve the precondition for each value of the domain. You add an action that is preconditioned by that value and achieve the new value. And you pay a cost for that. Okay, the cost is the difference between the maximal utility achievable for that variable and the utility of that value that you change. Okay, so as a result, optimal solutions for an OSP task that you start with will correspond one-to-one to optimal solutions for the reformulation MCF planning task. The second reformulation is much more complicated, and I will spend a few more minutes on that. So first of all, note that there is an utility upper bound that is just the sum of maximal utilities per variable. You cannot achieve more than that. So looking at the OSP problem, you can actually change from the maximization to minimization by just doing the maximal minus the utility to achieve. And the second observation is that you can move utilities from states to actions in the case of SAS planning by observing that the difference between the state in which you apply an action and the state that results from applying an action is basically the sum over the effects of a difference between the precondition and the effect of that state. Sum of the effect variables of the difference between the precondition value and the effect value. Because in SAS, whenever the effect is defined, the precondition will be defined as well. So you basically can, so the difference is not dependent on the state, and then you can put this difference as the cost of an action. So then a plan would be a sequence of actions that takes you from initial state to the goal state, and the difference will be the difference between utility in the initial state and the utility in the goal state. So, and of course, since the initial state doesn't change, then it's independent of the utility of the initial state. So what you can do is you change from min to max, and then you need to just add. You don't change the problem dynamics at all. You just add another cost function that is equal to the utility of the action that you just computed. So in this case as well, the optimal solution is the optimal solutions for the OSP planning task correspond to the optimal solution to the MCF reformulated task as well. And note that the differences here can be negative, so that's why we need the cost function to possibly be negative. In fact, they usually will be negative. So let's compare. So the heuristic for soft goal reformulation, coming back to soft goal reformulation, is basically note that admissible heuristics compute another estimate of the difference between the utility upper bound and the best utility they can obtain. So the admissible utility overestimate is the difference between the upper bound on the utility and the admissible heuristic for the MCF planning problem. And then the MCF formulation heuristic is non-negative in this case. For the state delta reformulation, the admissible heuristic is compute the difference between the utility of the state and the best obtained utility from that state. And then the admissible overestimate is basically the difference between the utility of the state and the admissible estimate of the multi-cost function reformulation. And here the multi-cost function reformulation is non-positive. So obviously you can only improve from the state that you're in. So let's talk a little bit about the differences between the two reformulations. So for soft goal reformulation, we can use the SAS plan formalism, and that's not possible for state data reformulation. You have to stick to SAS formalism, and then if you start with SAS plan, then you need to reformulate the planning task. For soft goal reformulation, it has additional actions, and it changes completely the causal graph structure. While for the state delta reformulation, you have exactly the same actions, you just have additional cost function, and therefore it's the same causal structure. And of course, for software reformulation, that means that you have a larger state space, and for state delta, it's not. It's exactly the same state space. And the last point is that, well, while for for state delta we need negative action cost, with soft goal reformulation we don't, right? So it's only non-negative. So when you need to apply your classical planning heuristic to one of those formalisms, well, there are trade-offs, obviously. So let's move to the evaluation. We applied merge and shrink to state delta reformulation, merge and shrink to soft goal reformulation, and LMCAT to soft goal reformulation. I'm not going to talk about the details of how to actually apply it to multi-cost function planning. The details are in the paper. It's not that complicated. We compare to the blind branch and bound, and it's all in branch and bound search. And we are comparing on 4 suits that are built from classical, from IPC benchmarks, with having a bound as 100%, 75%, 50%, or 25% of the best solution cost that we had for that problem, for each problem. And here are the results. So basically, as you can see, we still lose mostly to the blind branch and bound. But I think that's an initial result that actually takes us in the right direction, and we can, with additional improvements of the heuristic values, we can, of the heuristic computations, we can get to better results. If you look at the per instance results of initial state estimate, that you can see that we actually get better estimates than really improve over the blind, obviously. It's just is not translated into coverage yet, but it will. So if you looked at if you've been at our HSD presentation of the paper with Emil, then you would see that once you move to A star, it actually improves the coverage, and you can improve it even further with some optimizations. So to sum up, we present two reformulations into MCF planning that allows us to easily adapt existing heuristics. We have exemplified with two of the classical planning heuristics, and the results still need improvement. And as I said, there are some better results for A-star search that are currently in HSDIP. And for future, there are several directions. One of them is some specific methods for constructing emergent shrink abstractions that result in informative estimates. And while operator counting heuristics were covered in Dominic's master thesis, there are other heuristics that can be adapted, and we should see how these heuristics perform. So if you have any ideas, I would love to hear them. Thank you. Questions?
Okay, we can ask Michael a few questions before we head out for lunch. Yes.
So you said the things are available. Where can we find them? Because I haven't seen a link in the paper.
I will send you the link. Yeah, you can send me an email. I will send
Thanks.
you a link to the code.
So initially you said that there's also previous work, but you don't have the code or the implementation for it to compare yourself against other approaches. Do you have an insight how you might compare, or how their approach might compare to yours?
My hunch is they more or less perform like that. I haven't seen any approach that outperforms branch and bound with blind search up until now.
Okay, anything else? Well, okay, let's defer all the other questions to the breaks. Thank you for being here, and bon appétit.